Okay, so let's now give the floor to Sonia Kanan. She's going to introduce us the project PECSYS about solar hydrogen production. So Sonia, I give you the floor. And she's from research engineer at group leader at Helmholtz-Zentrum Berlin. The floor is yours.
Sorry, I was muted. Thank you very much. I hope you can see my slides.
Yes, it's okay.
Very good, thank you. I would like to talk about the results of the PECSYS project, which ended last year, actually. And these are the other colleagues who are involved in the project. So in that case, we are looking at photovoltaic-driven water electrolysis technologies for green solar hydrogen generation. So as usual, I have to put a disclaimer that all the information shared here doesn't reflect the views of the European Union, and they're only our own. So the PECSYS was started with some targets for hydrogen production rates, solar to hydrogen efficiencies, device stability, and also costs of hydrogen, as you can see here. And the project lasted 4 years, from 2017 to 2020. And it involved 6 partners: the Helmholtz-Zentrum Berlin, Forschungszentrum Jülich, Uppsala, CNR from Italy, Enel Green Power, and Solibro. These 2 companies were solar cell manufacturers, whereas the rest were 3 research centers and a university. So actually our system was of a relatively low technology readiness level. I think we started at around 3 and ended at 6 in some cases. So our motivation was to scale up and prove the technical feasibility of directly coupled PV electrolysis. These are kind of systems without intervening power electronics between the 2 systems. And for this case, in some cases, we also wanted to understand the effect of variable solar radiation and thermal management of these systems. Because with variable solar irradiation and no power electronics, it means that also the electrolysis is running at variable operating conditions, unlike conventional electrolyzers. And also, in order to reduce the costs, we decided to reduce and simplify the balance of the plant on the electrolyzer side to allow modularity. So that means that you could use several units to scale up flexibly as you'd like. And then, as I already mentioned, we eliminated the power regulating electronics, but this required carefully matching and optimizing the capacities of the PV and electrolyzer over a wide variety of operating conditions. And then in some cases, we also looked at thermal integration of both subcomponents to benefit from the opposing temperature response. In this case, PV works better with cooler temperatures, while electrolysis works better with higher temperatures. And since we were not heating our electrolyzers actively, we were trying to use the waste heat from the PV cells to heat the electrolyzer in some cases. And the whole purpose of this was to exclusively use the incident solar energy to provide both heat and electricity to reduce the carbon footprint of the whole system. So in this project, we looked at various technologies and materials investigated, because we'd started off thinking that we look at several and then do some sort of silo and pick out one. But some external conditions forced us to decide to look at everything. And I think in the end, it was a good idea. So on the left-hand side, these are the adapted PV directly coupled systems with thermal integration. we have a smaller system based on thin film silicon and the alkaline electrolysis, which was thermally integrated. In this case, also the thin film silicon acted as a photoabsorber and was in contact with the electrolyte. Then we had two others where the PV module was separated from the electrolyte by a barrier, but still in thermal contact. And in one case, we had a system using copper indium gallium diselenide, and in another, silicon heterojunction solar cells. So you can see that the size starts increasing in this direction. And these three systems were using alkaline electrolysis and were only using nickel, molybdenum, or iron-based catalysts. Then on the right-hand side, this was the, let's say, the more mature systems as far as the electrolyzer is concerned. And these were also using well-known commercial PV technologies. In this case, this was using a silicon heterojunction mini module connected to a PEM electrolyzer directly, and also taking advantage of the albedo effect, because these were bifacial solar cells. And with this one, we're able to achieve efficiency of solar to hydrogen efficiency of 13.5%. And in the final system, which was the demonstrator, there were two types of PV modules, commercial PV modules. In the foreground, you see the silicon heterojunction PV modules, and in the background, copper indium gallium diselenide heterojunctions. And at the back of these were PEM electrolyzers hinged. I will show the details of this demonstrator in the next slide. So, so here again, we see our demonstrator, which was around 10 meters squared. And on this slide, on this picture, you see at the back of each PV module, there was a PEM electrolyzer directly hinged on it. So that makes it some sort of modular system. So you could just pick one of these modules and you have a full solar hydrogen generator. So with this system, it was the water was fed only through the cathode side. No pumps were used. There was no active heating or cooling of the electrolyzer, and there was no power electronics. And this system was run for around 6 months, or a little bit over 6 months. We had an average efficiency of around 10%. And this compares quite well with the others that I could find in the literature as far as operation time and efficiency. So all in all, if we compare the systems that were developed in the project with those in the literature, the details of the references for these points you can find in this paper, which also summarizes the project results. And here we have the solar conversion efficiency as a function of solar collection area. And of course, if you're moving in the top right-hand corner, represents systems with the highest capacity because they are the highest area and also highest efficiency. And these circles here show systems that were developed in the PECSYS project. And you can see most of our systems are moving towards the desired region. You can see that the blue dots are systems using non-platinum group catalysts, and those with the red symbols are using platinum group catalysts. And the field symbols are indicating thermal integration, and the ones which are not sealed, which are not filled, are with our discrete systems where there is no really thermal integration. But you can see that in most cases, of course, the better performance is always with platinum group catalysts for water splitting. And also in some cases, like for example, this small system here, the PV absorber is using 3/5. And in our case also with the systems with the these samples here were using copper, indium, gallium diselenide. And of course, this is also the scarcity of indium could be a question if you want to go to larger areas. Of course, we could have got a better efficiency if we were using, for example, anion exchange membranes. But at the time we started the project, such membranes were not really readily available. And therefore, we were quite limited in the current densities that we could achieve. And then, of course, we had a lot of problems because of corrosion, not only in the systems using alkaline, but also in the systems using water. And this is something that we require in the future to find materials which are corrosion resistant, also for seals and the like. So to summarize, we looked at different directly coupled photovoltaics and electrolysis approaches, which were spanning different levels of technical maturity and component integration. And we found that thermal integration significantly boosts the efficiency and production. And the systems that we developed really show for compared to all other one-sun devices, performances which is among the best in class and capacity for each class, for each approach. The details are in this paper. However, the durability of the electrolyzers requires more research. We had quite a bit of problems with trying to get the electrolyzers to work under fluctuating conditions outdoors without power electronics to control the power level. And then in order to scale up all the concepts, we need to look for different materials that are easy to, first of all, widely abundant, but also easy to process into high-performing components in order to reach higher technical maturity at a reasonable cost. Thank you very much for your attention, and I also thank my colleagues for their contributions to the work, and of course, the European Union for the funding of this project.
Thank you very much, Sonia, for this presentation. So I have two questions. At the end, you said that we need to work at the material level, but at the PV level, but also at electrolyzer level.
Yes. Mm-hmm.
And have you seen some specific, I don't know, degradation, or do you see some specific material development at the electrolyzer level with this configuration with PV and?
Yes, right now there's a lot of work in the catalyst world trying to look at the dynamic behavior of the catalysts in response to fluctuating input power that's typical to renewable energies. And so they are looking to see if they can take advantage of metastabilities of the state of the catalyst using inoperando testing to track the structural and let's say coordination of the catalyst, just to make sure that they find a way of preserving the active sites despite fluctuating conditions. This is what makes our let's say catalysts maybe slightly different from those of conventional electrolyzers, where the power level is somehow kept constant.
And I have one question from the audience.
Yes,
why are so many points with both PGM and thermal integration so low in efficiency?
These ones, sorry, this is why I said that I have to refer you to this paper. These are based on photocatalytic materials, and these are the materials where the photoabsorber is directly in contact with the electrolyte.
Okay.
And so usually they tend to be wide band gap materials. So already they are quite limited in the absorption of the solar spectrum. And then yeah, then of course the efficiency is quite low. And then they have to use platinum group catalysts maybe to achieve some reasonable performance out of them.
And I have a last question. The yield seems interesting, but I found out that the hydrogen flow rate is still low. For example, for a 10 square meter PV panel demonstrator, you produce 2.3 grams of hydrogen per hour and per square meter. Therefore, I was wondering about the application of such a concept.
Yeah, such a concept is really for a small. It's for decentralized small to medium users of hydrogen, but one of the partners, Enel, is looking at trying to expand this into maybe smaller, let's say mid-sized industries who supply their own hydrogen as they require.
Okay, thank you very much, Sonia, for this nice presentation. I will now give the floor to Vincent Pocheux,